Good morning, everyone, and thanks for joining. My name is Saurabh Kulkarni. I work at Meta, and today Jordan and I will be talking about developing a mobile card for data center fluid servicing. So, what is the motivation behind this? As the industry moves towards liquid cooling hardware, one of the main questions is, how do we service and maintain this type of hardware in our data centers? And the solution that we are talking about today is a mobile service card. This paper focuses on providing guidance on how we can approach this design and the various important considerations we need to take into account when designing such a system. So, before we dive into the details of the design and capabilities, let's take a quick look at the data center side of things. So, first and foremost is drain and fill. Now, if a liquid cooling hardware fails in the data center, like a liquid cooling rack, the mobile service card should be able to purge all the liquid out and then fill it with fresh coolant on the replaced hardware. Now, since we are talking about coolants and fluids, it must be ensured that we have the necessary safety controls and leak detection. In the event of a leak, the system should be able to shut itself down completely and alert the user of that leakage. In addition to this, whatever coolant we are using should be compatible with the materials that we use in the mobile service card. The mobile service card will have a reservoir that will carry this coolant. The volume of the reservoir will depend on how much purging and charging you need to do to service your liquid-cooled hardware. In addition to this, if the service card itself needs some kind of maintenance, like cleaning or removing all the reservoir fluid, there should be some kind of space in the data center if this is done on-site. The next important consideration is mobility and size. The size of the card will depend on the number of components it has and the size of the components itself. It will also depend on how much space you have in the data center. It must be ensured that when this mobile card is moved around, it is not damaging any of the equipment. In addition to this, ergonomic considerations need to be taken into account such that it is easy for the technician to use this card to service liquid-cooled hardware. Finally is interfacing with racks. Now, like I mentioned for drain and fluid, this mobile service card will connect to a liquid-cooled hardware using hoses or quick disconnects or whatever. For that, it should be ensured that there is compatibility between these two systems for that connection. So with all these different data center requirements in mind, let's turn towards the capabilities and design of this card. For that, I'll hand it over to Jordan.
Thanks, Rob, and thanks for that context on the need for this in a liquid cooling data center, especially around cold plate cooling. So I'm Jordan Johnson, mechanical engineer at Intel. As Rob mentioned, I, over the last year, actually led the design on a cart similar to this for liquid cooling liquid cooling testing within Intel labs. We then identified this need for a cart like this within a liquid-cooled data center to perform the same functions of fluid maintenance. So what I want to first go over is just some of the key core capabilities that would be required in any sort of cart like this, and then briefly go over some high-level design considerations. So first on the key cart capabilities. Any cart within a data center to really functionally meet those requirements Rob was pointing out must be able to flush fluid, charge fluid, as well as purge and dry any fluid loops. And brief background on this, so flush would just be using any sort of rinse fluid or even the cooling fluid itself to push out any old cooling fluid, any contaminants to clean your system. Charging would be maybe you're bringing a rack online, need to charge it with new cooling fluid, and then purge and dry for any sort of maintenance or decommission of a rack using air, compressed air, or nitrogen to push out any old fluid and also dry for decommission. Now I'm going to briefly go over an example piping diagram on how to meet these capabilities. This is just an overview right now. You can see there's kind of a charge loop on top with that green line. On the bottom is that rinse loop with the blue line, and then that purge in the middle. And I'll go in a little more detail, show each capability and how this could work with this high-level piping instrumentation diagram. So first on the flush cycle, the idea here, and I have the control panel, kind of front panel there in the top, an operator could press a momentary switch that would simultaneously open the pump and fluid valve in that rinse cycle. And what this does would then push that fluid through to the manifold and then ultimately through a bubble trap to ensure there's no air within the fluid that you're pushing into your rack, and then through a filter so that there's no contaminants, and also a flow meter, so the operator knows the speed at which the fluid is entering your rack or your liquid-cooled system. One thing I intentionally left out here, I'm not showing where the fluid leaves the rack. That ultimately is up to the data center operator where they want their fluid to end up. Is it going to be, water reuse, some sort of disposal system? That is entirely up to the data center operator and what their specific requirements are. So next is the charge cycle. It is essentially the same. Operator pushes a different momentary switch, opens the valve and turns on the pump, and then goes through those same three, bubble trap, filter, flow meter, those key components. What I do want to point out here is the ability to recirculate back into that reservoir. So as I believe Saurabh mentioned, you have to make sure you have enough room in your reservoir to fully charge your system. Now, being able to recirculate allows you to maybe shrink the size of that reservoir because you can just continuously recycle until the equivalent of 3 to 5 times the volume of your server or your blade of fluid has gone through to ensure there's no air bubbles and that it's fully charged. The last cycle I want to touch on here is the purge and dry cycle. So in this case, compressed air, that could be maybe facility air, compressed air within the cart itself, maybe compressed nitrogen. But ultimately, the key point here is having some sort of pressure regulator, filter for that air so that you are not introducing contaminants to your system, and then it goes out through that same outlet through the rack. So now with the remaining time left, I just want to hit on some of the key design considerations and maybe some of the trade-offs that need to be considered when designing a cart like this for the data center. First of all, and I'm sure you've heard it in a lot of other talks, material compatibility and pressure rating for every component is absolutely crucial to understand. Every component must meet or exceed whatever pressure rating for the fluid system that this cart is going to be used with. Additionally, the material compatibility, there should not be any concerns about corrosion or contaminants or any sort of adverse reaction with the cooling fluid used and then the materials used within the cart components. Performance, I don't want to get too deep into this. I just do want to call out when you're sourcing a pump for this cart, the way you'd look at the performance curve, what pressure head it produces, at what flow rates, and compare against your system pressure drop curve through your system. You do have to take into account with the cart, there's going to be additional pressure drop inherent through all those, flow meter, bubble trap, everything in there is going to have pressure drop inherent in the system. And so in sourcing those pumps, that needs to be taken into account and subtracted using some sort of fluid flow equation through pipes. Once that's predicted, source the pumps. Again, it would be good to test this cart against the actual system before deploying to multiple data centers. Next trade-off and really important design consideration is size and mobility. So I'm showing here the size of the cart that we use in our Intel liquid cooling testing. For our needs, it had to fit under a bench to stay out of the way of our, the tight lab size constraints. But this is where really the data center requirements are going to define the size of the cart. Mobility is super important to be able to service various racks throughout the data center, but size ultimately comes down to those trade-offs between reservoir size you want, are you going to have compressed air on it, and all sorts of different considerations. The next thing I want to cover is drip containment and detection. So Saurabh mentioned there should be leak detection that shuts off flow if there's any sort of leak. But this is where that trade-off really comes in with the size and mobility. Maybe your requirement is to have full containment of any fluid that could be contained within the cart. But of course, that is going to raise the size of your cart, potential added weight. It could be harder to push around. So then on the other end of the spectrum, and what I'm showing here is a simple drip tray. You have a leak rope in there, potentially just shut it off if there's any fluid detected there. The last thing I do want to touch on is control and usability. There's a lot that could be talked about here in terms of ergonomics, but all I want to talk about briefly is the kind of what we found to be a good answer for this is putting all the electronics in a centralized location above the fluid for safety, and then having everything clearly labeled. So every momentary switch clearly labeled for the operator has those switches, circuit breaker, as well as flow meter readout so they can determine the speed of the fluid entering the system. There is another thing. I show a picture here of the back of the control box with some switches. I'd have to direct to the white paper. There's some more information on maintenance and using the cart for self-maintenance, like Saurabh had mentioned. You would likely only have one of these in your data center, and so if you need to service the fluid within the cart itself, it should be able to do that on its own. So with that, call to action, similar to what Sean had shared earlier. Please check out this contribution. This is still pending final submission to the contribution site, but I urge you to read that white paper, look at some more in-depth design considerations in designing a cart such as this. And then also, please get involved in this cold plate sub-project group. Meets monthly. This is where all this kind of cold plate innovation and incubation happens. With that, are there any questions?
Yeah, if anybody has any questions, please walk up and take a mic. We have a few minutes here. They did a good job catching us back up on schedule.
Okay, that sounds good. Steve Harrington, Childyne. How often do you think you're going to need to replace the coolant in a rack-based system? Is that what you're talking about?
There's serviceability. I know that there are some people collaborating on actual material compatibility and defining that in a later white paper. I'm not going to speak towards maybe how often that would have to happen in a data center, because it really depends on the fluid and the materials in that loop.
Oh, okay, so that's the whatever the fluid specification group.
Right.
And last time I was there was no chemists on the group, so it wasn't really getting anywhere.
I think Sean might have a little better
answer
great. For you.
So yeah, we kind of looked into this. It's Steve, right?
Yeah.
Yeah, we kind of looked into this, Steve. So the two main options we're considering is treated water versus inhibited glycols. On the treated water side, you're more worried about the biogrowth. So 7 days is what we got back from some of the fluid suppliers we talked to, where you want to kind of get rid of any stagnant fluid. And then for the glycol, it's more just like the shelf life of the glycol itself, because it's biostatic. The glycol's above 25% volume. You don't worry about biogrowth as much, so it just kind of has that extensive shelf life. But we do have folks like Dow and Nalco now is contributing members to the OCP, and they can further take some of those questions if you need.
Okay,
Thanks.
I think we have time for one more, if there is one.
Okay.
Otherwise, we're good, and we'll see everyone back here at 11.
Thank you.
Thank you.
Cool.